Hello everyone. Today we are going to study self and mutual induction along with energy of energy stored in magnetic field. So let us start. Let us start with self induction. Here we can observe a coil and this through this coil AC current is flowing. Okay. So suppose when the current flows through this coil, it changes the magnetic field through this coil, and hence the magnetic flux linked with the coil also changes. Due to this, an EMF is induced in the coil. The phenomena is called self-induction and induced EMF is called self-induced EMF. So, as we have seen in the earlier slide, we had considered a coil, and through this coil, current is flowing, say I. The magnetic flux linked with this coil is directly proportional to the current flowing through it. So what we can say, phi is the magnetic flux and I is the current flowing through it. So phi is directly proportional to I. Means magnetic flux is directly proportional to the current flowing through the coil. So when we know when this proportionality sign moves, we can introduce a constant, and this constant what we introduced is L. So the equation becomes phi is equal to L into I, where L is known as coefficient of self-induction. So if the current changes with respect to time, then the magnetic flux also changes. So we can write that induced EMF is equal to minus d phi by dt. That is rate of change of magnetic flux. But we know phi is equal to L into I. So we simply going to replace this phi by I. So our equation becomes minus L into di by dt. Okay. So we can write the equation as induced EMF is equal to minus L into di by dt. Or simply we can write L is equal to induced EMF upon minus d phi by dt. And we can produce an statement for coefficient of self-inductance. And the statement becomes the coefficient of self-inductance is the ratio of EMF induced in the coil to the rate of change of current in the coil. Now let us see the mutual induction. We can observe this part is similar to that of the self-inductance. The only thing we added over here is this another coil. Okay, so in this mutual induction, what is happening? We have two coils. This is one coil and this is the another coil. The two coils are kept near to each other, and when the current in one coil, suppose the current through this coil is changing, then what will happen? EMF will be induced in this coil, this neighboring coil. Okay, current is flowing through this coil, but what will happen? EMF will induced in the neighboring coil, and this phenomena is called mutual induction. So how can we say? When two coils are kept near each other and current in one coil is changing, then EMF is induced in neighboring coil. This phenomena is called mutual induction. So the magnetic flux phi S. Phi S is the magnetic flux in the neighboring coil. This neighboring coil we can call as secondary coil. Okay, so the magnetic flux linked with the secondary coil completely depends on the current flowing through the primary coil. So we can write that phi s, that is magnetic flux linked to the secondary coil, is directly proportional to current flowing through the primary coil. So this equation, that is phi s is directly proportional to IP, can be written as phi s is equal to m into IP. What we had simply done, we had introduced a constant m, which is nothing but the coefficient of mutual induction. And when the EMF is induced in the secondary coil, we can say d phi by dt is equal to minus dip by dt, because EMF induced in the secondary coil is nothing but minus d phi by dt, and we have replaced this phi s by m into ip, and the equation becomes minus d phi s by dt is equal to minus dip by dt. So this equation we can write as induced EMF is equal to minus m into dip by dt, or we can simply write m is equal to induced EMF upon minus dip by dt. So from this equation, we can make a statement for coefficient of mutual inductance, and it can be written as coefficient of mutual inductance is the ratio of EMF induced in one coil to the rate of change of current in the other coil. Now let us study energy stored in magnetic field. Okay. So for this we have drawn this diagram. In this we have a coil L and current is flowing I. So to study energy stored in magnetic field, we'll try to understand some of the things that magnetic field can be of permanent magnet or electromagnet. Both magnetic field can store some energy. Permanent magnet always creates the magnetic flux and it does not vary upon the other external factors. But electromagnets creates its variable magnetic field based on how much current it carries. The dimension of this electromagnet is responsible to create the strength of magnetic field and hence the energy stored in this electromagnet. So as we come to know that, it would be okay for me to understand the energy stored in magnetic field, and for that we consider the electromagnet, that is a coil of large number of turns as we have shown in the figure L. This coil or indicator is carrying current I when it is connected across a battery voltage source through a switch. Suppose battery voltage is V volts and the value of the indicator is L Henry, and current I will flow at steady state. So when the switch is on, current will flow from 0 to its steady value. But due to self-induction, a induced voltage appears, and this induced voltage can be written as E is equal to minus minus L into di by dt. Okay. where this E is always in opposite direction of rate of change of current. Now, the energy or the work done due to this current passing through the inductor is U. Okay. And if we consider it as U, as the current starts from its zero value and flowing against the induced EMF E, the energy will grow up gradually from zero value to U. So we can write du is equal to W into dt, where W is the watt, or we can say W is small power. So W is nothing but minus E into I. So we can write energy stored in the indicator as du is equal to W into dt. Now simply we are going to substitute the value of W, that is minus E into I. So the equation becomes du is equal to minus E into I into dt, where we can write this equation as L into di by dt. E is nothing but L into di by dt into I into dt. So the equation becomes L into I into di. Simply what we'll do, we'll integrate this equation and we'll get U is equal to integral 0 to I Li into di, and this will gives 1 by 2 L into I square. Now we know that L is equal to nu 0 n square A upon L. As per the dimensions of coil, n is the number of turns of the coil, A is the effective cross-sectional area of the coil, and L is the effective length of the coil. Again, capital I is nothing but HL by N, where H is the magnetizing force and N is the number of turns of the coil and L is the effective length of the coil. So simply we can write this I as B into L by mu 0 N, and by substituting these values in the equation, value of L and value of I, we can get U as mu 0 n square A upon 2L into dl by mu 0 n whole square. And when this equation is simplified, we can get the answer as B square into A into L by 2 mu 0. So the stored energy in a magnetic field that is a conductor can be calculated from its dimension and flux density. So with this, I conclude. Thank you. Thank you so much.